100 meters below the surface of the Earth, at the Swiss-French border near Geneva, lies a large hadron collider. It is the world's largest and most powerful particle accelerator. It boosts protons to incredible speeds, close to the speed of light. In fact, it is a circular particle accelerator. The protons follow a roughly circular path, traveling in a complete loop 10,000 times every second. With each new turn around the circle, the protons gain energy until they reach the maximum energy the accelerator can provide. But that doesn't mean that the proton's energy is being boosted everywhere in the ring. In fact, when they complete one full turn of the LHC, the protons have been deflected 1,232 times, meaning that their trajectory changed while their energy stayed the same. But they've only been accelerated 8 times, meaning that their energy changed while their trajectory stayed the same. Why is there such a big difference between those two numbers? In this video, we'll talk about electric and magnetic fields and how we need both of them to design a particle accelerator and control a beam of electrically charged particles. This video is the first in our 3-part mini-series on electromagnetism. Make sure you watch them in order. This is number 1. We'll start by showing manifestations of the electric force and of its counterpart, the magnetic force. Then we'll see how these forces find their origin in the electromagnetic field. We'll use a model experiment to figure out the most important characteristics of these forces. In the end, we'll see how we can use them to control the trajectory of electrically charged particles in the LHC. Let's begin! Here are 2 pieces of tape. When we bring them together, they just hang vertically and sort of ignore each other. Now we're going to stick them on a glass surface. Let's make sure they are well attached to the glass and let's pull them away from the surface very sharply. If we bring them close to each other again, the ends of the tapes repel each other. And that's really different from the beginning when the tape stayed very straight. Let's do the experiment again. But this time, let's stick them on top of each other. Let's make sure they stick together well, then we take them off the glass plate and pull them sharply apart from each other. Let's make sure the non-sticky sides are facing each other, and this time the tapes are immediately touching. They are attracted to each other, and that's completely different from the 2 previous situations we saw. We've just created an interaction between the 2 strips of tape, which can either be attractive or repelling. We call it the electric force. Now, this might sound a little weird that 2 pieces of Scotch tape would have anything to do with electricity. So, let's figure out how those 2 very different things are connected. In ancient Greece, people observed that the same kind of interactions happened between various materials when they were rubbed together. In particular, they realized that amber, which is fossilized tree resin, can attract small, lightweight objects when rubbed with wool. Other materials attracting or repelling small objects were said to be charged like amber. And the Greek word for amber is electron. So, this new property came to be known as electric charge. Today, we know that electric charge is a fundamental property of the elementary particles which make up matter, just like their mass, for example. In an atom, you find neutrons, which have no electric charge, protons, which have an electric charge of +1, and electrons, which have an electric charge of -1. Since the number of protons is equal to the number of electrons, the net electric charge of an atom is 0. So typically, objects around us are neutral. They have no overall electric charge. When we rub 2 objects together, a transfer of electrons can happen between the atoms making up the objects. So one of the objects ends up with more electrons than before, leading to an excess of negative charges, and the other ends up with fewer electrons than before, leading to a lack of negative charges. When there is a lack of negative charges, we often speak of its consequence, which is that there is an excess of positive charges. So, in the first experiment with our strips of tape, there was a transfer of electrons between the glass surface and the tapes. It is not important where the excess electrons ended up, in the tapes or in the glass. What matters is that both tapes got charged the same way. In this case, we saw that they repelled each other. So, like charges repel. In the second experiment, there was a transfer of electrons from one tape to the other. Again, it's not important to know which tape ended up with more electrons. What matters is that the two tapes got charged in opposite ways. And in this case, we observed that they attracted each other. So, unlike charges attract. You might be wondering how many of these excess electrons we stripped off the tapes in those experiments. It turns out it's an extremely small number. Only about 1 in 10 to the 13 atoms in the tape lost or gained an electron. That's 1 in 10 million. That's an incredibly small fraction of all the electrons in the tapes to begin with. To really grasp how small a fraction this is, let's imagine that we represent each atom by a person. Well, we would need 1,000 times the population of the Earth, so 1,000 times 10 billion people, before we find just one person who stands for an atom which has lost an electron. And yet, such a small number of excess electrons in the tape is able to generate a force which moves another piece of tape. And yes, a piece of tape is kind of a boring object, but you have to realize it's an object we can perceive at our scale as humans. That's much larger than the scale of elementary particles. If just 1% of the atoms in both tapes had lost an electron, we would end up with a huge repulsive electric force between the tapes. A force with the same strength would be able to lift almost any object around us. For instance, it could lift one of the tapes, no questions asked. It could actually also lift an elephant. It would also totally be enough to lift the weight of an entire mountain. In fact, it would be able to lift something as heavy as our entire planet. So, in the end, the electric force is huge compared to the other force we experience on a daily basis, the gravitational force. In this video, there is a super small number of excess electrons which moved from the fur of the cat to the balloon. And that's enough to lift the balloon against the gravitational pull of the entire Earth. And clearly, the cat is both mind-blown and confused by that fact. There's one last thing we need to discuss about the electric force. Some materials, called conductors, allow electric charges to move freely through them. For example, all metallic objects and some water solutions are good electrical conductors. When there's a motion of electric charges through a conductor, that's what we call an electric current. Other materials, called insulators, do not allow electric charges to move through them. So, if an electric charge imbalance is created on their surface, for example by tearing or rubbing, those charges just sit there and don't go anywhere. And when we have electric charges that are not moving, we call them stationary or static. Our houses are full of manufactured products made from plastic, rubber or paper. They're insulators, which are really good at creating static charges through friction and at holding them there. So, we get to experience static electricity pretty often at home. For the Greeks, static electricity was a rare and specific phenomenon. They basically only had amber as an insulating material coming from nature and acting like a plastic. In this chapter, we'll talk about the magnetic force. It's sort of the companion of the electric force. Now, a word of warning. What we're going to discuss now is probably not what you have in mind when you think about magnetic objects. We are not going to talk about traditional magnets, at least not just yet. We'll get there in the end when we wrap up the series, so make sure you stick around to watch the last video on electromagnetism. We will start with an experiment which will help us reveal the magnetic force. Here are two strips of aluminium connected by electric cables to a power supply which can deliver a large electric current. In this configuration, the current runs in the same direction in each wire. When we turn on the power, we see that the wires attract each other. Let's watch that again. In this other configuration, the current runs in the opposite direction in each wire. And the wires repel each other when the power is on. Let's watch it again. So this time, we've created an interaction between the two aluminum strips, which can either be attractive or repelling. Now, this interaction only occurs when an electric current runs through the strips. Whether there's a current or not, the aluminum strips don't hold any excess electrons. They are electrically neutral. So, the force we are witnessing now cannot be the electric force we talked about earlier. But what we know about it so far is that it arises when electric charges are in motion. This new force is actually what we call the magnetic force. Now, again, this can be a little puzzling that two wires with a current might have anything to do with magnets. But we can do another version of our little demonstration to figure out how those concepts are connected this time. This time, we replaced one of the strips with a magnet. When we run a current through the other strip, the aluminium strip is really strongly attracted to the magnet all of a sudden. Somehow, we've made the aluminium strip magnetic when a current runs through it. So, electric currents and magnets do seem to create the same type of force. We are starting to see that magnetism and electricity are related. In fact, we now know that static electric charges create the electric force and moving electric charges create the magnetic force. So, the electric and magnetic forces are similar because they are both caused by electric charges, but they are also very different when you look at the phenomena they cause in our everyday lives. So different, in fact, that it took until 1865 and the works of Scottish physicist James Clerk Maxwell to understand that they are not two completely different things. Since then, physicists consider the electric and the magnetic force as two components of one single force, the electromagnetic force. Figuring out that they are, in a way, two sides of the same coin is still seen today as one of the greatest achievements of science. In the previous two chapters, we talked about forces acting between pairs of objects. How exactly does one object in the pair interact with the other without touching it? Or what happens to just one strip of tape with an excess of electric charge or to one aluminium strip carrying a current? There would still be something around that single object, it would still be affecting the region of space around it. That something, the fact that the properties of space are now different depending on where you are, is what physicists call a field. And actually, you've seen other fields before, for instance when watching the weather forecast. If I say, this afternoon, it will be 9 degrees in Bergen, 19 in Berlin and 25 in Athens, that's a temperature field. This specific property, temperature, has a different value depending on where you are, and the temperature field describes how it varies from one spot to the next. Fields can change with time. The map of temperatures over a country at night is very different from the same map in the middle of the day. Temperature fields are kind of simple. They represent how a property characterized by a single number, like 9, 19 and 25 degrees, varies through space and time. But some fields are a bit more complex. They represent properties characterized by two numbers, strength and direction. You've probably seen this already on wind velocity maps. On any given spot, the wind can blow in a given direction with a given strength. That's depicted with little arrows. For instance, here, over the North Sea, the wind goes from west to east with a speed of about 10 meters per second. Over the Baltic Sea, it goes from south to north, but also with a speed of about 10 meters per second. Same strength, different direction. Enough weather forecasting for the day. Let's get back to the topic in hand. In our case, we say that the excess electrons on a strip of tape create an electric field, and the moving electrons in a strip of aluminium create a magnetic field. Electric and magnetic fields are a bit like wind velocity fields because they have both a strength and a direction, and can be represented by a series of little arrows. And just like the respective forces, the two fields are two sides of the same coin, the electromagnetic field. In general, we say that electric charges create an electric field, and if they're moving, they also create a magnetic field. In turn, static electric charges feel the effect of the electric field, and moving electric charges also feel the effect of the magnetic field. To understand how fields work a little bit better, let's consider a static electron. It creates an electric field around it. The field is stronger close to the electron and weaker far away from it. If we place a second electron in the electric field, there will be an electric force on this second electron. The theory of electromagnetic fields is the best model physicists have come up with to explain how in both of our experiments the strips of tape and aluminium can sense each other at a distance. They interact through the electromagnetic field created by electric charges. In this chapter, we're going to figure out the properties of the electric and magnetic forces. To do that, we'll study how a beam of moving electrons is affected by electric and magnetic fields. Here is the device that will produce our electron beam. If you're old enough to have lived through the era of early computers, it might bring to mind some old memories. In fact, that's exactly what was inside the bulky television and computer monitors that were used back then. The most visible part of the device is this big glass vessel shaped like a funnel or like an old-fashioned light bulb. Inside the tube is a near vacuum. It only contains a small number of neon atoms moving around. At the small end of the tube is a piece of metal which we can heat up. If we dim the lights, we can see it glow. It is now emitting electrons in the vacuum inside the tube. Some electrons make it through the hole in a second metal piece and come out in a straight line like a beam. And we can actually see where they go because some of them hit some of the lonely neon atoms. And after such a collision, the neon atoms produce an orange light. So this light materializes the path of the electron beam. The wide end of the tube is coated with a material which glows green when hit by the beam. You can see that right now the beam is hitting the center of the tube. Side note, both of these forms of light, the orange one and the green one, correspond to the release of energy from excited atoms. That's luminescence. For more on luminescence, watch our video How to Create Photons You Can See. Let's first see how the electrons are affected by an electric field. We can apply an electric field in the narrow section of the glass tube between these small metal plates. The field goes between them in this direction, so perpendicularly to the velocity of the electrons in the beam. Basically, one plate collects an excess of electrons, the other ends up with a lack of electrons, and an electric field appears in between them. So, whatever happens, the direction of the electric field is always going to be the same. But the strength of the field changes with time, and it does so according to this pattern, which we call a sawtooth wave. At first there is no field, then the strength increases linearly to a maximum value, then drops back almost instantly to zero, and then the pattern starts again. This is how the electron beam reacts to the electric field. We can see that the beam is deflected in the opposite direction from the field. The stronger the field, the stronger the deflection. Let's now see how the electrons in the beam are affected by a magnetic field. This time we'll bring our own magnet, a horseshoe magnet. These types of magnets are useful because they create very simple magnetic fields. The field is directed from one end of the horseshoe to the other end. And, as we said before, if you want to know how the field is created by a magnet like this, you'll have to watch until the last video in the series. This is how the electron beam reacts to the magnetic field. We can see that the beam is going up, so the deflection is in a direction perpendicular to the magnetic field. And the closer we bring the magnet, the stronger the magnetic field and the stronger the deflection. What's going on? It seems that our electrons respond to a magnetic field in a kind of complicated way. Okay, so now we have explored a very fundamental experimental system, so we should have gathered some clues as to how the electric and magnetic forces act on electrically charged particles. And actually, that was explained in full by the Dutch physicist Heinrich Lorentz at the end of the 19th century. That's why most of the time the electromagnetic force is also known as the Lorentz force. Here are some of the key findings from Lorentz. Let's talk about the electric force first and consider a static particle in a uniform electric field. The line of action of the electric force is parallel to the electric field. The force acts in the same direction as the field if the particle has a positive electric charge and in the opposite direction if it has a negative electric charge. So the electric force is relatively simple. Let's move on to the magnetic force, which is a bit more complex. Let's consider a particle in a uniform magnetic field. And this time, the particle has to be moving, because static particles don't feel the effect of the magnetic field. Let's start by talking about the strength of the magnetic force. When the particle's velocity is parallel to the magnetic field, there is no magnetic force at all. The magnetic force is strongest when the particle's velocity is perpendicular to the magnetic field. Now, let's talk about the direction of the magnetic force. The line of action of the magnetic force is perpendicular to both the particle's velocity and the magnetic field. That means it is not in the same plane as them. To visualize this better, you can use what we call the right-hand rule. If your thumb points in the direction of the particle's velocity and your index finger points in the direction of the magnetic field, then the direction of the magnetic force on a positively charged particle is given by your middle finger. And that's the final thing we need to know. The magnetic force acts in the direction given by the right-hand rule on a positive electric charge and in the opposite direction on a negative electric charge. That was kind of a lot to take in, so don't hesitate to go over the last section again if you want. What we just talked about is at the core of the work of engineers at CERN, who really need to know very well the effect of the electromagnetic force on a beam of charged particles. It's so important in our lives at CERN that we may or may not greet each other in the corridors using the right-hand rule instead of a handshake or a fist bump. At this point, we should know enough to return to CERN's giant accelerator, the LHC. In the beginning of this video, we said that the protons were deflected 1,232 times, but only accelerated 8 times in one loop around the LHC. Let's see which components of the machine actually do that, how they work, and why we need so much more deflection than acceleration. In the LHC, the protons move around in a 27-kilometer long pipe under near vacuum conditions. But this pipe is not shaped like a perfect circle. Some sections of the LHC are actually straight. In one of these straight sections, we find the accelerating components we just mentioned. They are called radio frequency cavities. The job of these cavities is to apply a strong electric field in the direction the protons are going just at the right time when a bunch of protons passes through them. The protons experience an electric force in their direction of motion. That's going to make them go even faster in that same direction. This increased speed is what you and I would typically call acceleration. In fact, in the LHC, the protons are moving extremely fast, almost at the speed of light. In this context, the radio frequency cavities can't actually speed them up by a lot, as nothing can go faster than the speed of light. So what really happens when they go through the cavities is that they gain more and more energy. That's what we mean when we use the term acceleration in this context. It's much more like a boost in energy than an increase in speed. If there was nothing after the cavities, the protons would continue on the same trajectory, in a straight line, and smash into the walls of the beam pipe, which bends around to form the ring of the LHC. But if you were to follow the beam pipe in the tunnel after the cavities, you'd find that soon after, the pipe gets sandwiched between the two poles of some other components called dipole magnets located inside those blue cylinders. Their job is to apply a strong magnetic field in the vertical direction. And why vertical? Because if the protons are going in the direction of your thumb and the magnetic field is vertical along your index, then the magnetic force is exerted along your middle finger. So, the protons experience a force perpendicularly to their direction of motion. That's going to curve their trajectory without changing their speed. It's what you and I would typically call deflection. But we have to be very precise about the words we use here. A physicist would actually also call this deflection acceleration. To understand why, imagine you're on a bike. You can pedal faster in a straight line, and that's going to make you speed up. You're changing the strength of your velocity. But you can also keep pedaling at the same rate and take a bend. That's going to curve your trajectory, meaning you're changing the direction of your velocity without changing the strength of your velocity. To physicists, acceleration is a broad term that covers both of these types of change to velocity. So that's why sometimes you might hear that the dipole magnets accelerate the protons. But if we want to make sure there's no ambiguity, let's just use the term deflect in that case from now on. So, the protons are deflected by the magnetic force. Actually, each dipole magnet only deflects the protons by a very tiny amount, 0.3 degrees. That means that after a 15-meter distance, the protons will have shifted by about 1 centimeter to the side. It may not feel like much, and such a small change of direction is barely noticeable to the naked eye, but in fact, it's already a huge achievement. The faster an object goes, the harder it is to change its direction, and the protons in the LHC are moving at a speed close to the speed of light. So, we need the dipole magnets to create super intense magnetic fields if we want to change the direction of the protons at all. In fact, it would take a lot of time and effort to make stronger magnets than the ones we already have. So, in the end, it is much easier to bend the proton's trajectory many times by a little bit rather than a few times by a lot. That means that our circular accelerator can't be very curved. And that means it should have a very large diameter, so large that the tunnel ends up being very long. That's why we need 1232 dipole magnets to make the protons go around one full loop of the LHC, and why a circular accelerator is mostly a circular deflector. So let's summarize what we've learned in this video. An electric force arises between two objects when they each have an excess or a lack of electric charges. Similarly charged objects repel, oppositely charged objects attract. A magnetic force arises between two metal wires when they are carrying an electric current. It is the same force as the one between two magnets. Electric charges create an electric field around them. If they're moving, they also create a magnetic field around them. Electric and magnetic fields are the two components of the electromagnetic field. The electromagnetic field acts on an electrically charged particle through the Lorentz force. It accelerates it in the direction of the electric field, and if it is moving, bends its trajectory in a direction perpendicular to both its velocity and the magnetic field, according to the right-hand rule. Both components of the electromagnetic field are crucial in the LHC. Intense electric fields are used to accelerate the protons. Intense magnetic fields are used to deflect the protons so that they travel in a loop. That's all for now. Thanks for learning with us. In the next video in this series, we're going to talk about magnets and currents and magnets. See you soon in the next video.